Welcome. After learning about the removal techniques for the gas hydrate, we shall be now looking into the estimation of the gas hydrate and various effects of the impurities on this gas hydrate formation. So, in this tutorial on the hydrate removal, we shall be learning about the estimation of the water content in sweet and sour natural gas, because water content determines the extent or the possibility of the gas hydrate formation, and also we shall be estimating the hydrate formation temperature. So, first let us look into the problem, that in this problem we have to determine the saturated water content for a sweet lean hydrocarbon gas at 66 degrees centigrade and at this particular pressure absolute. And also we have to determine the concentration of the water if the gas were sour with, this is the H2S content and carbon dioxide content. So, this is with 3.3% H2S and 1.7% of carbon dioxide, what would be the water content of the same gas. That means we find that without the presence of the carbon dioxide and H2S, we shall be having one type of water content, and in their presence the water content will be different. And in our lecture we learned that the presence of the carbon dioxide and this H2S generally decreases this water content. Now let us look at this, that here are the given situations. So, we shall be using the graphs which I showed in the lecture. So, here we find that this graph we shall be using, on this axis with the temperature, and on this axis we have the water content in terms of the milligram of water per standard cubic meter of the wet gas at 15 degrees centigrade, and about this 101 kilopascal, that is about 1 atmosphere. There are various lines of constant pressure. So, and these are the corrections for the CO2 and the brine. So, first what we shall do, that we shall locate our temperature pressure. So, here we locate our temperature, that is 66 degrees centigrade, and then we go to the pressure line and we find that this is the particular point where the given pressure and this temperature are coinciding, and at this point now we can go to vertically up either on this axis or this axis. So, find out the water content, and this comes to about 4500. If you go to this, we find this is about between 4000 and 5000. This is about 4500 milligram per standard cubic meter of wet gas. So, this is how we find out the first part of the question, that for a clean gas, non-sour gas, how we find out the water content. So, next we go for the correction for the relative density. Here we have the graph. So, how do we correct it? So, first we locate the relative density from this problem, and here we find the relative density is here and the temperature is 66. So, somewhere between the 10 degree and the 50 degree line curves, we shall be locating the temperature, and then we shall be reading out the value of this CG's correction factor 0.98, and then we shall be putting this correction factor with this one, and we shall be getting the value of this correction, this water content, and we find that by this correction the water content has now decreased. Now we go to the next part of the problem, that is to find out the water content in the presence of the H2S and the CO2. Now, for this we shall be using this particular graphs. Now, in these graphs we find that these graphs are given in terms of the pressure, temperature and the equivalent H2S content. Now, equivalent H2S content is given by this formula, that is the mole percent of the H2S plus 0.7 into mole percent of carbon dioxide. So, first what we would do, that we would be finding the equivalent H2S mole fraction, and this comes to about 4.49%. Now, to use these graphs, what we do, first we locate this 4.49, and we first locate the temperature here, and then we locate the 4.4. This is the various constant percent H2S equivalent, so 5, 10, 15 like this. So ours is 4.49, this is somewhere near this 5, and we have our temperature here. So wherever they are intersecting, from this intersection point we move up to the given pressure, and from the given pressure we find that somewhere here we have the pressure located, and we go to the y axis to read out the water content ratio that is given by the water content in the sour gas to the water content in the sweet gas. So we read out the ratio from this. Now please understand that for sake of understanding we have put very big dot here, but whenever you are solving such kind of problems you have to do it very fine pencil so that there is no smudging of the points. So here somewhere here we shall be finding the water content ratio. This we read out, this is about 1.05. So what we have to do, this particular ratio when multiplied by the water content in sweet gas will give us the water content in the sour gas. So here it is, the water content ratio is taken 1.05, and this is the one we have obtained for the sweet gas, and this is how we find the water content in the sour gas. And as I told you that the sour gas content, sour gas water content is more than that for the sweet gas because of the presence of the H2S and the CO2. Next we come to another problem which concerns with the determination of the hydrate formation temperature for some given pressure and for this kind of a natural gas. In this case we have been given the molecular weight here and the specific gravity of the natural gas. With these are the mole fractions of the various components. Now what we do for this, we have to use this particular chart. Here in this chart we find that we are given the temperature as these slant lines, and the relative densities are given, can be taken from these vertical lines, and these are the various pressures. Now what we do, that from the given value, this data, first we locate the this line for the various types of this percentage H2S, and here this 4.18 is the H2S percent. So we locate somewhere we have to locate this 4.18, and this the pressure is 4200. So this is 4000 and 5000. So this is the pressure line, and this wherever the pressure line is, it is not dissecting exactly on 4.18. So what we need to do, between 2 and 5 we have to interpolate to figure out where 4.18 lies, and this is the some point where this is 4.18. So from this intersection of this H2S curve and the pressure line, what we do, we go to the horizontally to find out the temperature here, and this temperature and also we have to also go for the specific gravity that is given as 0.682. So we find the temperature and this particular section, and now we know that these slant lines are the temperature lines. So we have to figure out some approximately, though we find these lines are not exactly parallel, for sake of approximation we make a parallel line corresponding to this line which is nearest to it, and then we extend it up to the temperature line. Now from this we can find out the value of the temperature about 70 degrees centigrade. Please understand, suppose these were lying in the at this nearby this particular thing, then we should draw the line parallel to this particular plot. So but suppose it is in between these two, then you may take an average by taking a line parallel to this one, and then you can take another line parallel to this one, and you will get two different temperatures, and you may take the average of these two temperatures to gauge the temperature for this particular hydrate formation. Now to give the correction for the presence of the H2S, what we do, for the presence of the C3 component in H2S, what we do, now first we locate this H2S that is 4.18, and then percentage C3 that is the propane is given as 0.67 percent, that is from here we somewhere between 0.5 and 0.75 will somewhere by interpolation locate this 0.67, and wherever it is intersecting, from that point we come down, and here we have the various pressures given. So from these pressures, wherever this particular vertical line is intersecting the given pressure, from that we read out the temperature correction on the y-axis, and this comes to about minus 1.5 degrees centigrade. And now what we do, from the 17 degrees formation temperature we deduct this 1.5, and we find that the hydrate formation temperature in presence of the H2S and the propane content is coming to 15.5 degree centigrade. So that is how we are able to adjust for the presence of the C3 component and the H2S for the hydrate formation temperature. Now what we find, the presence of these impurities decrease the formation temperature of the gas hydrate. Next we shall take up another problem. In this problem we are going to find out the dew point depression due to the change in the water content of the natural gas. So the problem is like this, that we have a natural gas which flows at this particular flow rate through a dehydrator at this 1000 psig pressure and at 100 degree Fahrenheit, and the outlet water content of the natural gas is given as this 7 pound of water per million standard cubic feet. Now here you have to see that the natural gas is getting dehydrated, and we assume that this 100 degree Fahrenheit is the dew point at which the dehydration is taking place, and due to dehydration the amount of water reduces to this value. So we need to find out that what would be the reduction or the decrease in the dew point, because as we know that with the change in the water content the dew point of the natural gas also changes, and as the water content decreases, so is the dew point. Now here comes the solution, that we are given all this data and we have to find out the dew point depression, and along with that we can also find out the water content at the inlet. So now we arrange all the given data and what has to be found out in this fashion, and we take note of this particular plot which has been given for the water content. Here we find on the x-axis we have the temperatures in both in terms of the Fahrenheit and degree centigrade, and here on the y-axis we are given the water content in terms of the pounds per million cubic feet at 14.7 and psia and 60 degree Fahrenheit. These are the standard conditions and these are the various pressure lines, and here we find this is the hydrate line. So this particular figure we also saw earlier. Now first we do what we do, that according to our problem we first figure out put the 100 degree Fahrenheit from this x-axis and make a vertical to the given pressure of 1000 psig, and then what we do, that here we locate at this 1000 psi line, we locate this particular point, and then from here we go to the horizontal line and go to the y-axis, and here we read out the value of the water content, which is about 60 pound per million cubic feet of the natural gas. So that is how we find out the water content in the inlet natural gas. So here we put the value as 60. Now to go for the dew point temperature, now what we have to do, we will use the same graph now with the water content as 7. So again we go to this graph and locate 7 on the y-axis and make a horizontal line which passes through the, wherever it intersects the 100 psig line, there we drop the vertical line and we find this is the temperature of the natural gas at the outlet, and now this particular temperature is about 37 degree Fahrenheit. So here we write that 37 degree, and this particular value 63 is the depression or the decrease in the dew point of the natural gas due to a decrease in the water content. And these are the some of the references from which you can know more about the hydrates and this topic. Thank you.